All right, hi everybody. Good afternoon. Good to see you guys. Hope you're doing really well. We're back at it. It's more critical thinking. Cal State Fullerton. This is our 1 to 2:15 p.m. Section. So welcome back, everybody. Hope you guys are comfortable and doing really well. Today we're going to finish up the notes on Chapter 12, the one that has to do with science. So that's the main goal. Try to go through those notes, and then you guys will be all ready and set to go for the quiz that's coming right up. So the next thing that's happening in the class in terms of your work is Monday the 20th. We have our quiz on Chapter 12. So this week's lecture is all about Chapter 12 in science. So all the key concepts, terms, definitions that we've reviewed this week that are found in our textbook, that's the kind of stuff that I'm going to use for our quiz of next Monday. And that's the last quiz. After that, there's just one more homework assignment and the final. And I'll assign for you guys the last homework assignment after the quiz. So, we'll focus on one thing at a time. For now, your main priority should be taking good, clear notes for the lectures this week, making sure that you either view these live streams or get a chance to look at the playback on it, read Chapter 12, take your good notes, and then have a successful quiz on Monday. After that, I'll give you guys your fourth homework assignment, and that's going to be due on Wednesday the 29th, and then it's just down to the final exam. So I'm working on finishing the grading for the last homework that you guys just submitted for advertising and marketing and the fallacies within ads. So that's going to be all done this week, and then you can ask for your score over the weekend by email, and I'll be happy to give any individual person their score so that you would know, if you like, where you stand going into that quiz. But anyway, that's the plan. It's Chapter 12. We finished that today. You have your quiz on Monday. Then the last subject of the semester is Chapter 9. That's going to be our last material that we have to review. So that starts up next Wednesday. And we have 3 lessons on that before we start to review for the final. So just a couple of quick updates, I guess, for anybody who's tuning in a little early. We still got about 4 minutes till class time. So I'll probably repeat some of those points once the hour starts, but I don't know. Those are just a few things on my mind for now, since I'm just getting the camera rolling. But let me be right back. Let me get myself a beverage to drink. All right. Hope you guys are doing well. At any point, obviously, feel free to just say hello. Questions, comments, movie suggestions, video game suggestions, jokes, anything, it's all welcome to me. Well, you will just ask me, Karina, for your grades. That's the way that I like to run things. I have my own electronic record-keeping system, but I don't do mass delivery of grades to all the students through any kind of interface. I like it to be one-on-one. So to any student that wants to know their grade, simply ask me. It's possible to calculate your grade by counting up the total points that you've been awarded from your different assignments and then dividing by the maximum number total possible. And then you get a percentage. But I have a current score for every student. Before this current homework that you turned in on Monday has received a score. I believe that means that there were 600 points so far in the class. So there's 200 for the final, there's 100 for the third quiz, there's 100 for the fourth homework. So there's 400 points that remain yet to be determined. The first 500 have been fully scored, and the 500 to 600 for this last homework, that's what I'm in the process of looking at right now. So any student that would like to know their overall grade or individual assignment scores for anything, simply could email me, and I've been replying to student questions on that just on a case-by-case basis. So you have to email me. That's how you'll get your grade. And then I'll reply to you, the individual, with your grade. Okay. Cool. Thank you so much, Karina. Hope you're doing well. Same with everyone else. just another minute or so, and then I'll go ahead and get us underway. Nice day out there, getting to some spring weather, so that's always a good moment in time. Hey, Sammy, good to see you too. Let's see. All right. How trippy is this? Little time delay. Let's see how long it takes. All right, interesting. I have another account that I'm using to monitor the lecture in case randomly, if there was ever like internet trolls or something, I could easily block them using the role of the viewer. You can block other commenters in the live chat, which is something I guess you guys would want to know just in case. If there ever was like a random person that we don't know from class, then you could simply block them by clicking the 3 dots that appear to the right of their text in the live chat there. But anyway, I know a couple of professors, colleagues, and friends of mine who've had a few horror stories of people, you know, hijacking Zoom meetings or whatever else. So there's always potential for that. But there is an unlisted way to make this live stream protected for only those that have access to a link. But it also makes it a little more complex to get everyone viewing it at the same time. And so unless that became necessary, I'm not going to go to the unlisted system with YouTube Live. But anyways, guys, back to class. Welcome here. Good to see everybody. Anybody that wants to say hi or just tap in at any point, just know that I'm always looking for your comments, and the feedback and the interaction always helps a lot for everybody, me and you and everyone else. So let's go ahead and continue. A couple of points that I was mentioning just a moment ago. Now that it's 1 p.m., I'll just repeat some of them to be clear. We have a quiz on Monday. That's quiz on chapter 12. We're following the syllabus dates just exactly, so no changes have been made. We do have a quiz on Monday, and it's on chapter 12, which is all about science. So the lecture this week from last Monday and today are the 2 lectures that you would want to focus on for getting prepared for this quiz. I've been grading the homework assignment that you just submitted, and I will have those grades ready before the end of the weekend. So my plan is to send around, hey Juliana and all you guys, my plan is to send a titanium message around Sunday morning to tell you guys, hey, the quizzes, the homeworks have been graded, and feel free to inquire for your score. So at that time, either Saturday night or Sunday morning, when I send the message out, everybody who wants their grade for homework 3 could simply send me a message, and I'll reply individually with your score. And if you want to know anything else, how you're doing in the class or whatever, be happy to talk to you about that too. So anyways, scores will be ready for the homework this weekend. Quiz 3 is upcoming on Monday, and that's all about chapter 12, science. The 3rd quiz is valued at 100 points. So the other 2 quizzes before it were 50 points. So it's a 10% quiz. The last one, because it's the last one, is worth twice as much. Anyway, then after that, the next thing would be homework 4, and I'm going to assign homework 4 on Monday after the quiz. So for now, you can focus on the quiz, and then after that, we will get your instructions up for the 4th and final homework assignment. That'll be due Wednesday, the 29th. Then after that, it's just the final, and we'll have 2 study guide review sessions, the 2 meetings during week 15, Monday and Wednesday, 4th of May and 6th of May. And then the finals during finals week. So yes, if there's ever questions about anything involving our schedule, our assignments, or anything else, do let me know. But I'm trying to be as thorough and transparent with you guys as I can be, so there's no surprises. We all know what to expect. Okay, then, well, back to chapter 12. Got a couple of leftover notes. I don't know if it will take the entire class period like it sometimes does, but we'll see how much time it does occupy, and then we'll be good to go for today, all right? So chapter 12 is all about science. chapter 12, science. And what we did at the beginning last class was just go over some of the initial big vocabulary items and concepts on this chapter. So we started by just defining science. And what is that? It's reasoning from observable facts to testable explanations for the facts. So a scientist looks at the world and using their five senses and whatever measuring or other instruments they may have to conduct observations of the world. By observing the world, some kind of phenomena is seen, which is not yet explained or understood. And then the scientist tries to provide an explanation for the occurrence of the phenomenon that could be tested by other people to determine that it's accurate. So that's trying to get testable explanations for observed facts. Wanting to know how things work, how cause-effect relations function, and why events occur in our environment around us. Not just having things happen, but having no insight into them, rather knowing why, so that we have the detailed understanding either for practical or simply for theoretical value. Say hi to Kitty again. She's always getting involved, right? We talked about a couple of the important figures in early history of science in the West. So we talked about Copernicus, who discovered the heliocentric model of the solar system, meaning that the sun's at the center and the planets rotate around it. And that replaced the older idea of geocentrism. It was kind of a fundamentally important discovery, this heliocentrism, which was enabled by newly invented telescopes, because prior to that, the church was seen as the dominant institution for all higher learning and knowledge, and therefore it was in competition with the church view that the earth had to be at the middle, because God would have definitely wanted humans to be in the most important position. Anyway, discovering that the earth's not at the center was considered heretical and unorthodox, but it showed that just by using empirical study and observation of the world, that we could come to true conclusions about it, that we're not guided by religious authority. So Copernicus is a big name. Also, we talked about Francis Bacon, who formalized and systematized the steps of the scientific method. So Bacon and Copernicus. After that, if you don't mind there, Kitty, may I? Is that all right with you? After that, we talked about some of the key assumptions that are built into science. So for example, one assumption is empiricism, the belief that our five senses are the primary source of human knowledge, and that by using them we can discover most all about the universe. Objectivity, that's the idea that we actually can learn about things as they really are in and of themselves, so that we can learn about the universe as it really is, and that we can come to objective truths about it without any bias. Then there's materialism. This is the view that everything in the world, in the universe, is made out of physical matter. So essentially all things are made out of atoms, even up to and including you and your consciousness. So everything's made out of physical matter, including us and our minds. And we talked about the assumption of predictability, that the world, the universe, is orderly and predictable. So established cause and effect relationships should repeat and be repeatable on and on into the permanent future. And then the assumption of unity, which is that it is believed that there's a single set of scientific laws and principles that could be used to explain the occurrence of all events from the largest to the smallest. Okay, then we talked about some limitations of science. For example, science is limited to the observation and study of things that can be observed. So if something is incapable of observation, like maybe dark matter or something like that, antimatter, if there's something incapable of being observed physically, either directly or indirectly, then it's going to be very hard for science to fully explain that kind of thing, since it's based on the observable. Another limitation of science is that it assumes the existence of the external world, which of course is a given assumption, but in philosophical terms, it's not possible to absolutely prove it beyond all possible doubt, since there's always the very remote possibility of having lived in a simulation or a dream or something like that. Okay, now let me ask quickly, did any of you guys remember my last few comments at the end? Didn't we talk about attitudes that people take toward the relationship of science and religion? Wasn't that part of our discussion? Did we have that little chat? I believe so, but if you could quickly confirm, that would be helpful. We talked about views that people have about the relationship of science and religion, or no? Did we? Good. Okay, Walden and Peter, and thank you guys, Jennifer. We talked about that. So I think we spoke about all four of them, right? So number one, some people say that if science disagrees with religion, that science should take priority over it. As it's written in the textbook, some say that when they come into conflict, science trumps religion. The word trumps being used as a verb, of course, not a proper noun to name the president. It's a funny word in a sense. The name or word trump, if it was used as a verb, means to like take priority over something else. So to avoid false associations with the president, which is not related to this topic, I just went with different verbiage. So some say that when religion and science disagree, that science should take precedence over religion. So if there's a debate or a conflict between the claim of evolution theory and creationism, then according to that first view, you'd break in favor of the evolution theory and reject the creation story. A second view is the alternative to that, which is the idea that when they come into conflict, religion should take priority over science. So if religion says that man was made in the image of God within the first 7 days of creation, but theories of science say no, there's a much more gradual process that took billions of years, and human beings were not fully formed but are the descendants of greater apes and stuff like that, then in the second perspective, you'd prioritize and favor the religious explanation and not the scientific account. The third idea would be that science and religion deal with different topics, so there's no conflict because they're talking about different issues. And the fourth view is that science and religion are actually compatible with each other, because although they appear to say different things, that's just because of a false interpretation of the religious scriptures. Maybe if we modified our analysis or interpretation of those doctrines, they would be saying nothing different than the scientist says. Now, most practicing scientists and a lot of people in the academy favor the first type of position, that science should be deferred to in disputes over questions that religion disagrees with. More traditional religious practitioners of whatever faith would be more like in the second camp. And then we have people that hold to the other possibilities. Next up then, since that's just the review that I kind of wanted to get through, we're going to move on and start talking about the steps in the scientific method. Okay, so the scientific method, something that probably by now we've at least heard about, but let's refresh our memory and take a quick tour through the steps in that method. So first of all, the scientific method overall is just identifying some type of problem and then applying observation and test to the explanation of that observed problem. Now, the three levels of critical thinking, we talked about that earlier in our class, and just going way back in the mind, let's think about those three steps again. So 3 steps of critical thinking begins with experience, just what happened to a person. After that, it moves ahead to the level of interpretation, trying to provide an explanation of why or how the event happened. And then it arrives at the step of analysis, where you go back to your interpretation and you reconsider whether it is actually the best one available, or is there a better one. Now, those steps of the critical thinking process mentioned in our book earlier in the semester, they bear some generic similarities or resemblance to the parts of the scientific method. Now, the textbook goes over the steps of the scientific method and it divides it into 5 steps. But we're going to go over all 5 of those steps. But for the time being, I just wanted to kind of call out the big 3 of the steps of the scientific method and demonstrate to you how there are some similarities between this procedure of critical thinking and then the procedure that we use in science as the scientific method. So scientific method well, how are there parallels? In the scientific method, you start off with an observation. Like you just observe something happening in the world. It could be a volcano erupting. It could be a hurricane hitting. It could be a person getting really sick and dying from some illness, right? You just observe something that has happened. but you want to go further from there and try and understand the reasons. So the equivalent to what we call interpretation here in scientific language is to create a hypothesis. And again, we're going to go back to these terms in the steps of the scientific method and provide a more detailed description of each step. But basically, you start by observing things, then you try and generate a hypothesis to explain why that thing did happen that you observed. But you don't just leave it at that. You don't just say, here's my hypothesis and I'm done. In science, the hypothesis gives rise to an experiment which tests the hypothesis. So, like in the critical thinking procedure, you have an explanation for why an experience happened, but then later on you might go back to that interpretation and say, is it really the best one? Is there something else that's a different interpretation that could provide a more suitable explanation? In science, there is that similar feature because you start just observing facts, then you want to try and create hypotheses which explain why those things happen. But to test your hypothesis, to see is it the correct explanation, in other words, you do have to generate an experiment, and the experiment will have the potential to either confirm or disconfirm the hypothesis. So I just kind of wanted to show you that there is some little level of similarity between the two procedures here. Critical thinking in general, whether it's deployed in a scientific context or in an everyday context, and then the work of scientists. In both cases, we start off by just noting that something has happened, trying to explain why, but going further and allowing ourselves to be critical of the initial attempt at an explanation. Okay, so having stated what the generic similarities are between the two, we're going to now go over those steps, as I said, in line-by-line detail. So the steps of the scientific method now. And we'll deal with each step one at a time. The steps in the scientific method. Okay, well, the first one, number one step is simply identify a problem. Okay, so by observing the world, identify some unexplained phenomenon. Okay. So that's our first step there, to identify a problem. In science, it's all about explanation, trying to explain why things happen or how they work. And that means you have to have a problem to explain. If there's no unexplained event or phenomenon, then there's nothing for the scientists to do. So you start off by just examining the world using your observation, and you try and identify something that we don't fully well understand yet. Let me give you some different examples of that. And I'm going to use my book too. Sorry. Okay, so here's an example. There's been this kind of noted phenomenon over the past 15 or so years of the number of bees in the planet Earth going on the decline. This has been noted and observed so widely that there are even terms to refer to it, like a bee colony collapse disorder. So what's the reason for that? We see these bees dying off, that the numbers of them globally are in decline. And in fact, more recent studies that I've read say that this is really not even so much limited to bees anymore, that we're seeing in a generic way leveling off of insect life across a whole bunch of different species. But anyway, let's just focus on the case of bees for a moment. Bees are in decline, and that's something that we can just observe. Now, at this level, the first step in the scientific method, we're not going beyond that to ask questions. Why is that happening? What's the real explanation? Just to identify that this is some problem and we don't yet know why. So now science has a job for us to do. Try and give us an answer to our question, why are the bees dying off in these great numbers? So you got your first step, and that's not the only possible example. There could be many others. Let's see in the book. I mean, thinking about it in terms of epidemiology and medicine, I mean, because we're dealing with a pandemic right now. Imagine that a lot of people just start dying and no one understands why. You could identify some problem there. You could say, well, we have unexplained incidents of mortality happening in different communities, and now we got to set out to try and explain the reason for that. Is it something environmental? Is it something genetic? Is it exposure to some type of toxin in the environment? Is it a virus or what? Okay, so we begin the process of science by looking at the world and finding things that we don't yet understand, or at least don't know why they're happening or what caused them to happen. But it doesn't end there, obviously. It moves to the second step. So let's go on. Step number 2 is to develop an initial hypothesis. Okay, so second step is all about creating the hypothesis that tries to give some explanation for the problem. So one states an educated scientific guess to explain the occurrence of the observed problem. Explain the occurrence of the observed problem from step 1. Okay, and just so no one's confused at all about the word hypothesis, it's used in this step 2, but I don't want to leave it undefined. So everyone understand what is a hypothesis in specific detail. It's kind of obliquely referenced here. It is an educated scientific guess to explain the occurrence of an observed problem. So what's a hypothesis? Educated scientific guess to explain an observed or identified problem. So that's the second step of a scientific method. We had a problem that we don't yet understand why it happened. Now we're at least trying to give some reasonable assessment of why. So it's kind of like an educated guess. It's not yet, claiming to be the only possible explanation, but it's an attempt. And when we have got our initial hypothesis, eventually we're going to try and put this hypothesis to the test to see whether it can be proven somehow experimentally. In the case of the bee colony collapse disorder, there could be many different competing hypotheses to explain that. Let's suppose maybe one view could be that changing weather patterns due to increased greenhouse gas accumulation. Maybe this is throwing off the life cycle of these bees or their ability to reproduce their numbers. Maybe this is the thing that's causing the result we're seeing. Or maybe another person says, I don't know, is that the right explanation? I have a different hypothesis. Maybe it is the creation of cell phone towers. The decline in the bee numbers seems to be roughly coincident with the advancement of widespread mobile technology. And so maybe it is the broad-scale deployment of 4G and 5G cell phone towers that's interfering with the, life cycle of the bee and causing them to die. These are different hypotheses, right? But once a scientist or researcher has established one, they try to go ahead and provide some detailed experiment that can test this later. I don't know, sea levels are rising around the planet Earth. You could say that's an identified problem, and there could be different hypotheses which try to give an answer as to why that is happening. It could have to do with an illness. It could have to do with a natural process of planet Earth or a geologic process. Could have to do with biology of other life forms or why they undergo certain changes. Whatever the case may be, a scientific hypothesis is given to once again give some type of reasonable estimation or guess as to why the identified problem is happening. Now, quick note about some terminology here. I want you guys to understand the difference between a hypothesis and a theory. You already saw the definition of hypothesis, which I just had written on the board. A theory is just kind of like a hypothesis that's graduated to another level because it's been very well confirmed and well proven by experimental findings. So a theory is just a very well proven hypothesis. So, you know, if you've had a hypothesis to try and explain the occurrence of some phenomenon, and you say, don't take my word for it, here, conduct an experiment and see if your experimental results confirm this hypothesis. By the time it has been confirmed, reconfirmed over and over again, replicated, as they say in science, in a variety of other settings by other researchers, the more and more times this theory gets confirmed by means of experiments, the more and more credibility that it has. So what starts off as a hypothesis, which is sort of tentative and admittedly something that could be contradicted by future empirical investigation and experiment, if it has been proven by many, many subsequent experiments and studies, then that adds credibility to it and it attains the status of a theory. So we talk about like the theory of evolution or theories of like physics, like the theory of relativity. These are theories because they've passed through the gauntlet of extensive confirmation by means of numerous different tests in different research laboratories or whatever. So you start off with a problem, you identify what it is, then you develop a hypothesis that attempts to explain why it happened. And if your hypothesis gets very well proven down the line, then it will become a theory. Now, the third step in the scientific method, because we've gone over just two so far, identify a problem, develop an initial hypothesis. The third step is to gather additional information to refine the hypothesis if necessary. So step 3, gather additional info and refine the hypothesis. So this is all about narrowing down, making a little more precise the statement of the hypothesis. So what this is really all about is after your initial data collection, you may need to make some slight adjustments to the hypothesis. So adjust the hypothesis if needed based on initial data collection. All right, so sometimes you have an initial hypothesis that has to be tweaked a little bit or slightly narrowed down in order for it to be the best hypothesis to put on the table for testing. Say, for example, we had the hypothesis that, so like we've had a lot of mass shootings prior to the pandemic. I guess now there's no way to get out there in public, but over the past 20 years, it was really like an epidemic of mass shootings happening in public places, schools, places of worship, right? Maybe this will continue when we get society back online, hopefully not, but it's certainly a problem, right? For public safety and for all those matters. Now, what could be the reason that we saw such a spate of shootings in our country that wasn't really seen in a lot of other industrialized countries, including some where there's access to weapons? One person might have said, "Oh, I think it has to do with video games that people are playing. Maybe video games are causing people to conduct these shootings." So that's the person's hypothesis, right? Maybe they start to gather a bunch of data and they see that there's video games being played everywhere, and maybe it just has to do with specific types of games. Like, I don't know, they narrow their hypothesis down to first-person shooter games like Doom or whatever, and they think maybe it is some type of previous exposure to games like this at a person's early life that predisposes them to be a likelier candidate to commit, some type of public crime like that. I don't know. I'm not saying I believe that. In fact, quite the contrary. I'm an avid gamer, and I know that these games are played well in many countries where we don't have the same rates of mass shootings or gun violence. But anyway, some people have tried to put forward such ideas. If they did, then they might have to refine the hypothesis based on the initial collection of data. I don't know. Let's see. Take the case mentioned just earlier that there's bee colony collapse occurring across the planet. Maybe the person's initial hypothesis has to do with exposure to radiation in the atmosphere. But when they start to study which kind of radiation has emerged in the last 20 years where the phenomena has been more widely seen, maybe they think it has to do with the specific frequency of it. Like, it's not just radio waves, maybe it has to do with microwaves, or maybe it has to do with 5G towers as opposed to 4G towers, right? So the hypothesis may be altered, amended, modified based on the initial collection of data. But suppose now that you have your fully robust, refined hypothesis, and you want to see if it's correct. That takes us to the next step, which is probably one of the most important of all. That's step 4, where you test the hypothesis. So we're still just going over the steps of the scientific method. There's 5 of them. We talked about the first 3. Here's number 4. Just simply test the hypothesis. So when you test a hypothesis, what you do is, either in a real world or like a laboratory setting, you conduct an experiment which can be used to either confirm or disconfirm the hypothesis. All right, so either in a real world or laboratory setting, one conducts an experiment to see whether the hypothesis is correct. Okay, so you got to test the hypothesis. You can't just throw an idea out there like, maybe this is the reason, and then say, but I have no evidence. That's just how I feel today. You have to be able to somehow test that hypothesis with experimental means. So I'm working off of the one example mentioned in the book, so I'm going to go back to that. Take the case of the hypothesis that bees are dying in great numbers because of global deployment of cell phone towers. Now, if that is a person's hypothesis that the radiation given off by cell phone towers somehow causes the decline of bees, in order for this to be tested, you'd have to be able to control that variable, and then you'd have to be able to determine whether or not the introduction of this variable or not creates an outcome that is predicted by the hypothesis, right? So how do you think that might work? Let's just sort of walk through a possible test of this. The person's claim is bees will die if cell phone tower radiation is exposed to them at a certain level. How do you think that could be tested just in terms of designing such a test? You'd have to get what? What would be the materials? What do you think? So how could one test that hypothesis? The hypothesis is, I think the bees are dying because of cell phone tower radiation that they're getting hit with. How could a person create a test? Should we just take the person's word for it? Of course not. But how do we test whether they're getting the right explanation? What would you put out there or suggest for this test? Just so we all are on the same page, clearly understanding the idea of a test. Test is used to see whether this is a true or false hypothesis. So how could that one be tested? Maybe. Let's see what you think. So make a closed chamber of the bees and have the cell phone tower radiation available for emitting into that closed environment. So you could have a control group, right? You could have one group exposed to the dependent variable of some isolated cell phone tower radiation that can be beamed in there. And then you have another control group where that variable is not given, where they're not exposed to such radiation. Now, if the hypothesis is correct, then what should be the outcome to the one colony of bees that's exposed to the radiation? Well, if the hypothesis is correct, then what it should predict is that the exposure of that radiation to the bees should lead to the decline in their numbers. So if you see that, then that aligns with the predicted outcome of the hypothesis. And in that case, the hypothesis has been confirmed by means of the study or the experiment. But of course, it's not it's not a foretold outcome that the hypothesis will be verified, because of course it's possible that you have the wrong explanation. If you do have the wrong explanation, then the test will be able to show that. In this case, the test would result, if it's not the right hypothesis, in there being no measurable effect on the bees when they're exposed to the dependent variable. So, the hypothesis is either going to gain confirmation or disconfirmation from the test, which brings us to the final step of the process. So step 5. I said in a real world or a laboratory setting because, like in some cases where you study things, you don't necessarily create a laboratory experiment. If I have a hypothesis which says something like people who played too many of these certain types of video games are likelier to commit mass shootings, then it's not like I'm going to be able to get a human being and make them a test subject and just sort of pump their head full of these video games and then watch if they go out and commit shootings. But what I could do is study the statistical facts concerning each case and then dig into the case histories through their files to see whether or not that prediction bears out the actual cases that we've seen in the past. So that would be like looking in the real world rather than creating a controlled study. But both methods can and are used in order to arrive at scientific conclusions. Okay. Sometimes we do a lot of these tests with little rats and mice when we want to study things that where we have a common physiological structure to them, like to study the effect of certain addictive substances. We might expose a sample group of lab rats to it to see how that might affect predictably their behavior or their sociality or their health. So these experiments can be conducted in a wide variety of possible settings, either in a lab or by means of data that's collected from the real world. Now, the fifth and final step of the scientific method is this one. It's simply where you evaluate the hypothesis based on the results of the test. So evaluate the hypothesis based on testing results. Okay, so imagine that you've gone all the way through the process. You saw a problem in the world, like, why did that happen? You came up with a hypothesis trying to explain why. You collected some initial data to start working towards the experiment, and maybe you made a couple of little small adjustments to your hypothesis. But now you test it, and we've got the results of the test. That takes us to the final step where you evaluate the hypothesis based on the test results. So there's two outcomes that are possible from your testing of the hypothesis. It's either going to verify the hypothesis or it is not. So let's talk about what happens in either of those two outcomes. If the experiment verifies the hypothesis, if the test confirms the hypothesis, then that's success. So in that case, then you publish the results for further confirmation by other scientists. And on the other hand, if the test disconfirms the hypothesis, then let's talk about that. If the test disconfirms the hypothesis, then go back to, now I'm going to ask you a question. Go back to step, all right. So imagine that, your hypothesis didn't actually get verified by the test you did. Like, for example, you thought that cell phone tower radiation was harming the bees and resulting in their global decline, but you conducted an experiment and you pumped them full of a bunch of that cell phone radiation, but nothing happened and the bees are just doing fine in there. So that's not confirmation of your hypothesis. That seems to show that this is not the proper explanation. In that case, what step do you think you got to go back to in the procedure of steps 1 through 5? You got all the way to step 5, but at that point, your test did not show that you had the right hypothesis. So which step do you think you'd go back to at that point? You can tell me the number if you can, or say the label of it. You would return back to step 2. That's correct. It's not step 1. It's not that you observe, the problem still exists. So that's not it, Eduardo. It's like the problem of bees declining is still an objective fact. We just haven't yet come up with the proper explanation of it. Still the same problem to be explained, but we need to find a different explanation for it. And in that case, you go back to step 2 to design a new hypothesis and then run through the steps again until you finally get to a hypothesis which is confirmed by the results of your experiment. Okay, and then you've had a successful result. The hypothesis is matched by the predicted results of the test, and now you can publish that study. And when that study hits the scientific community, other researchers are going to try and replicate the same experimental findings. And if they do so in their own, then wider and wider reconfirmation and duplication of results is going to eventually lead this hypothesis to attain the status of a theory. And that's when we think we will have arrived at the correct explanation for the problem we identified way back at step 1. Okay, so that's the way the procedure works. It starts by identifying problems, trying to give explanations, reasonable, scientific, educated guesses to explain them, refining those hypotheses, putting them to some type of test, and then at the outcome of the test, determining whether or not it verified or did not verify our hypothesis. If it verified it, published it, and send it out to the others to examine on their own. And if it's not confirmed, then you don't have the right hypothesis yet, so it's time to go back to not square 1, but I guess square 2, and try and find a better hypothesis. So that's the way that the process goes, and we can therefore erase this part. And I just have a little bit more information for you guys about qualities of a good scientific theory or hypothesis. So what are qualities of a good scientific theory? As we've said, and as we kind of have just learned, not all hypotheses are equal. Some are more accurate to the proper explanation of the problem they're trying to explain. So how can we distinguish between the case of a good hypothesis or theory and one that's not so good? By looking at and considering factors like these. So I'm putting up here qualities of a good scientific hypothesis. Or we can say theory. Because if it's good, then it's probably already on that level of being a theory. Okay, so what are some of those qualities? All mentioned in our book. First of all, there's just relevance to the problem being studied. Okay, so I mean, in a way, I thought this is almost so obvious that does the book really need to say that? But fair enough. If you have a hypothesis or theory, but it has no relevance to the problem that you're trying to explain, then that can be disregarded immediately. Suppose that I'm interested in why there's more hurricanes happening now than, let's say, 15 years ago, and why are there more powerful hurricanes happening now? And then I try to say, well, maybe it has something to do with the coronavirus. You know, maybe the coronavirus is causing these hurricanes, but this is completely irrelevant. They're two completely separate questions. One has to do with weather, and the other has to do with the science of viruses and sicknesses. So the one thing bears no significance or has no bearing for the purposes of the problem that you're trying to investigate. Some people do formulate hypotheses that are wildly off base, that have no connection to the subject matter of the thing they are trying to explain. Like if a person says that, you know, something socially is the cause of something that's happening in outer space, that could not possibly have any connection. So make sure to check that the hypothesis is at least within the ballpark of relevance of the topic that you're trying to study and investigate. Second quality of a good scientific hypothesis / theory is consistency with well-established theories. With other well-established theories. Okay, so let me explain that with a brief little description. What it means is a good scientific theory will fit in with and will not contradict others that have been well proven before. So a good scientific theory will fit in with, and this is really the key, not contradict other well-proven theories. So about science, it's supposed to be built on the results of earlier work. It's not like with each new generation we say, let us eliminate all the scientific progress that we ever made in the past and replace it with completely new ideas that don't have any logical connection to the old stuff. We think of science as an ever-growing body of knowledge that is built on the earlier results that have come before. So generally speaking, a good scientific theory has to not contradict all the other stuff that's already been well proven. Say, for example, I don't know, I have the theory that the way that my presents arrive under my tree on Christmas is from Santa Claus. Now, for me to accept that theory, I would have to hold that he's able to fly in the sleigh and deliver the presents from this reindeer-driven sleigh that flies through the air. But for that theory to be correct, I would have to completely reject everything that we think we know about gravity, about aerodynamics, and about the flightless terrestrial mammals that we call reindeers. So we would have to completely reject our idea that no, those animals can't fly given their physiological structure, know that an object unsupported in the air without a mechanism of propulsion cannot suspend itself above the ground. We would have to reject long-standing and extremely well-proven theories concerning gravity and biology. So although that's a hypothesis that one could put out there, it's not a good one because it doesn't sit well with other stuff that's been very well proven. So for a theory to be a good one, it's got to kind of fit in to the body of existing scientific theories and not contradict it. It's supposed to build on top of it, but not replace those already well-established ideas. Let me see what's in the book on this point. It says much the same, but I'll just read it off. It says science is a system of logically consistent hypotheses or theories. Scientific explanations are preferred if they are consistent with well-established theories in the field, what the American historian of science Thomas Kuhn refers to as normal science. So they give this example of the evolution theory as opposed to the intelligent design or creation theory. It says, the intelligent design theory does not meet this criteria because it is inconsistent with the well-established theory of evolution. So when you have a theory, it has to be judged in the light of the existing body of knowledge that already has been well proven by science. Now, it's not impossible for there to be a revolutionary theory that completely overturns a long-standing scientific consensus. But the thing is, that's generally thought to be the exception, not the rule. For example, Einstein's theory of relativity does in fact contradict principles of Newtonian physics that we thought were absolutely certainly true. But the power of Einstein's theories and the confirmation that has been achieved for them through experimental results is so compelling that it's kind of overwhelming evidence, which leads us to have a paradigm shift. In the absence of such overwhelming evidence that an existing theory is to be rejected, we ordinarily want to hold on to them and simply expand on ideas that have already been put forward before to bring in new theories that don't contradict, at least, what has already been proven through scientific methods or established to a high degree of confirmation. Okay, so that is another quality of a good scientific theory, to be consistent with well-established theories, to not contradict them. All right, so we have a couple more points on this topic of qualities of a good scientific theory. The next one is the quality that is sometimes called simplicity. And I want you to know that the textbook labels it under the term simplicity, but sometimes when this is described, you'll also hear it referred to as Occam's razor. Okay, so Occam's razor. Okay, now here's the concept that we're currently discussing. It's this idea that if you have multiple different hypotheses, which all are trying to explain one phenomenon, the simpler one of them is the likelier to be true. So the simpler of two proposed hypotheses or theories is likelier to actually be correct. The simpler of two theories or explanations is likelier to be correct, likelier to be true. Simpler of two theories, likelier to be correct. That is the principle of simplicity, otherwise known as Occam's razor. Why is it also known as Occam's razor? There was this medieval philosopher named William of Occam, British philosopher of the medieval period of world history, and he said this initially, and that idea has kind of become well established within the practice of science. So say we've got two explanations for a given event. One of them, though, is way more complicated. It involves way more additional assumptions than the other one does. The basic rule is that whichever of the two explanations that involves fewer assumptions and is thus simpler is the one that is likelier to be true. This is based on the idea that the universe is somehow parsimonious and it operates in an elegant and uncomplicated way. So the simpler of two proposed explanations usually always amounts to what the truth is. Like, here's an example for you. Maybe it's not a perfect example, but we're going to try. Suppose that one day after, I don't know, we used to go out in public a lot, but let's say, you would gone somewhere in a car, and it's your car. Suppose that after you finished doing whatever you were doing, after you parked and did some stuff, you come back to where you had parked and the car's not there. When we used to have class face-to-face meetings, I would say, hey, you guys, imagine if you go back to the parking lot and your car's not there. Well, let's use our imagination and think of another similar example. You go to the grocery store, and when you go back out to the lot, the car's not in the lot. Okay, so that could happen to somebody. Now, what could be one possible hypothesis about what happened to the car? You know, put your scientific reasoning hat on for half a second while imagine that situation unfolds. What's the problem? Well, the identified problem is my car's not where I left it. So now some explanation could be given. What do you think could be a possible explanation, a simple explanation for that? Car's not there. I know where I parked it. It's not there. That's a problem. What could be a person's initial hypothesis for that? There's a couple of possibilities, but let's see what you might throw out there. Where's the car? What could explain? Maybe what? I don't know. You just got to give me a guess. What do you think? Okay, maybe one thing is it's towed. Walden, you're throwing out maybe parked it somewhere else. Okay, I can see both of those possibilities of hypothesis. Let's go with the towing hypothesis for now, because I just want to have one to compare with another one that's a lot weirder. So, you know, person gets to the parking stall. They had a clear memory, let's imagine. You're saying sinkhole, that's another one, Jennifer. There's also theft. That's a possibility, Peter. We've got a lot of hypotheses on the table right here. But I'm just going to go with the first one I saw, which is towing, because I think that's probably what your initial instinct might be if this really did happen to you. Unless, I don't know, living in a really bad neighborhood where there's a lot of theft, maybe you'd have that hypothesis. But they're both fine. Let's just assume that let's go with towing. So, you know, you get back to the car, it's not there. Where to go? Maybe it was towed. That's my hypothesis. Now, suppose that there's another hypothesis that's also available. The second one is, could it be that the aliens took the car? Maybe aliens came down and they abducted this car and took it back away in their spaceship. So that's where it's actually at. Now we got two hypotheses. One, towing. The other, alien abduction. Now, which of those two do you think would be the simpler of the two? It's easy to say, but just let me know. Which is simpler? A simpler, less complicated, more straightforward explanation for that. Out of the two that I gave you. Towed, taken to outer space by the aliens. What's simpler? Just the first one, that it was towed. That's much simpler because how many extra assumptions do you have to make for the second one to be true? Well, for the second hypothesis to be true, you'd have to assume all these other things that you don't have to assume with the simple towing hypothesis. You'd have to assume that aliens exist, which is an open question. You'd have to assume that they have the means of transport to reach the planet Earth from whatever distant star they orbit around, and that's also complicated. Then you'd have to assume, third, that they want to come specifically to the Earth and that they have an interest in your car for whatever reason, among all things. Now, that's very weird and out there, and it's a pretty far out scenario for that to be the right explanation. So I'm kind of making it very extreme. One is a straightforward, common sense explanation. The other one is very weird and it's so complicated. But in general, whatever there are two explanations for something, the simpler one is the one that is preferred by science and the one that is likelier to actually be correct. So you can sort of just take that to the bank in everyday life. You know, if you have a very complex explanation for why something's happening, but there's a simpler one that's also suitable to the facts, then the simpler one is likelier to be true. Now, it's not 100% saying that in every single case, the simpler explanation won't be true. I mean, if a very clever criminal committed a crime and planted a bunch of evidence that made it seem like a completely different person did it, then maybe investigators would look at the evidence and say the simplest explanation is that individual B is the culprit, when in fact individual A, who they don't know anything about, is the one that's arranged all the evidence. But, you know, in the general case, someone being framed is less likely than for the evidence to have been deposited by the commission of the crime itself. So, you know, hypotheses, as far as they go, are likelier to be true when it takes fewer assumptions to sustain the truth of the hypothesis. And that's what it says here in the book. So, if rival hypotheses both satisfy the other criteria, scientists generally accept the one that is simpler, a logical principle known as Occam's razor, named for the medieval philosopher William of Ockham. The great majority of scientists reject intelligent design theory because, among other things, the theory of evolution is simpler than that of intelligent design. The process of evolution, scientists argue, can explain the gradual development of complex organs such as the human eye, But to assume intelligent design, you have to assume that there's more than just a natural universe, and that there's a supernatural being who somehow intervenes in the course of natural events in order to construct the life forms in a way consistent with the intentions of the creator. So that's Occam's razor. And we just have a couple of more points on this. So simplicity, we've discussed. Next up, what's called falsifiability. Okay. Falsifiability, the word just means able to be proven false. So a good scientific theory is capable of being proven false. And that might seem a little counterintuitive at first, but it's true. So a good scientific theory is capable of being proven false. Now that doesn't mean that it is false. It just means that there is some way in theory for it to be proven false if it actually was. If a theory is not falsifiable, then it's unscientific. Because if it's not falsifiable, that means that there's no way, even in principle, to demonstrate that it's false. And the only way that you can test the truth of a hypothesis is if you understand what a falsification condition would look like. Because it's only against the contrast of it not being falsified that one can gain confirmation for it. So if you don't know what would count against the theory being true, then you also don't know what counts as proof or confirmation for it. And therefore, it would be merely a suggestion, but not something that is a scientific hypothesis. For example, in the case of the bee colony collapse cell phone hypothesis, is that falsifiable, that it's caused by cell phone tower radiation? Yes, it's falsifiable. That's the whole reason that a test is given. The test falsifies that hypothesis if the predicted result of exposing the bees to the radiation does not occur. That would count as falsification of that hypothesis. Here, a maybe simpler example. If I have a hypothesis that because every swan that I've ever seen was white, that all swans are white, can the hypothesis that they're all white be falsified? Yes. What would be the way to falsify the hypothesis that all swans are white? If a person what? What would be the thing that would show that's not true? That would make sure that we understand it is false, the hypothesis all swans are white. That could easily be falsified if we ever came across what? A black swan, yes, or any non-white swan. In fact, initially, for a long time, people who studied swans did think they were all white because the black swan's very rare. But all it took was the existence of one swan that was non-white to falsify that hypothesis. So there has to be a way of finding out that the thing's not true. Now, if it is true, then the falsification condition will merely remain hypothetical. Like if it was false, we would have seen this, but we don't. But if we don't even know what to look for in principle to determine that a hypothesis or theory is false, then it cannot be tested either. Let me give you some examples of hypotheses that are not falsifiable. Take, for example, the horoscopes, like that say, according to our whatever insight into the orbits of the stars and the constellations above, given the time of your birth and date, there are certain predictions that we can make about what's likely to happen to you. So you read your horoscope for a given week or something, and you think this is the predicted outcome. Say that's the hypothesis, that you, being a Pisces or something, are going to have like some kind of friend come visit you this week. Now, can anything falsify that? Not really, because if you say to the astrologist, that prediction didn't come true, then they will simply reinterpret what the prediction means and therefore deny that you had falsification. So if you say, oh, look, it said I would be visited by a friend this week, but I wasn't visited by anybody. They'll just say, I don't know, maybe you just weren't looking hard enough, buddy. You know, did you notice that little bird that perched on your windowsill that was singing in the morning? I mean, that's all it meant. It was a little bit of a metaphor for a friend. A fine feathered friend is what we meant here. But look, in that case, they're not allowing you to say, no, I have disconfirmation. Nothing can be given that counts as disconfirmation according to this pseudoscientific practice of astrology. So it's not actually a scientific hypothesis because nothing can be done to test it, and no disconfirmation is possible. Let's go in another direction. Sigmund Freud. Some of you guys may have ever heard about this man. He's considered one of the great fathers of psychoanalysis, right? But his ideas, many of them have been criticized. Like, I think one of the only surviving ideas that's kind of retained relevance is the existence of the subconscious mind. But he did have these weird thoughts about like you having proto-sexual desires for your opposite sex parent. So he said, you know, the little boy has a latent sexual attraction to the mother figure, and that is the Oedipus complex. And the little girl has a latent sexual attraction to the father, and that is the Electra complex or penis envy or any of those things. Now, if you challenge Freud's ideas and say, there's no way, I'm not attracted at all to my mom, or if you're a woman, to my dad, you know, what's your evidence that I am? And he would say, oh, it's just, you know, those are your impulses that are subconscious. And if you say, well, I don't have those impulses, he would say, okay, well, that's just because you're repressing them, you know, you're repressing them into your subconscious mind. You just can't tell that you have them. Now it looks like there's no possible way to disconfirm these theories, because even if you say I don't have such drives, they'll simply be denied that you don't have them, and they'll be claimed to exist in your subconscious mind. So here, as I read it here, it says this. For example, Sigmund Freud's theories about the Oedipus complex fail the falsifiability criteria, because if a man says he does not have this complex, Freudians argue that he has just repressed it into his unconsciousness. However, unconscious thoughts by their very nature are not testable, so therefore there's no way of falsifying Freud's theory. Now, a good scientific hypothesis is falsifiable. Take, for example, the work of Albert Einstein. He said that according to his theories of relativity, a predicted outcome is that a massive object should be able to actually bend and curve light rays that occur from behind it. So he said, if this is true, then the next time we have a lunar eclipse where the moon blocks the sun from behind it, then what we should actually be able to see is some of the sun rays bent around the surface of the moon from the planet Earth, because the massive surface of the moon will actually warp the light as it tunnels around the sides of it. He said, next time we have an eclipse, let's see if this observation of the light signal from behind the moon can be witnessed on the Earth. And if you can't see it, then maybe my theory is wrong. So he doesn't just say, take my word for it. He says, look, here's a prediction of the theory, and the theory is falsified if the prediction doesn't turn out to be true. But of course, the next time there was such an eclipse, the exactly predicted outcome was seen, and so falsification was not obtained. But falsifiability was presupposed by even being able to conduct the experiment. Okay, so scientific theories have to have a condition of being proven false. Does not mean they are false, but it means that we have something to look for in an effort to prove that it's true. So not seeing the falsification outcome counts as confirmation. But if we do not know what a falsification outcome would have been, then we don't even know how to confirm the theory, and thus it's unscientific. Okay, now just a little more on qualities of a good scientific theory. Next up is what's called predictive power. Okay, so predictive power, and this is the last of these qualities of a good scientific theory, so that ends that section of the notes. All that's being said here is a good scientific theory is able to accurately predict the occurrence of similar events in the future. Okay, so a good scientific theory can be used to accurately predict future events. So how good is a scientific theory? Well, another thing that enhances its quality of being good is the extent to which it's able to accurately supply us with predictions of future events. Take just a simple case like weather, the study of weather and meteorology. When the weatherman or woman tells you, here is the forecast for the next 7 days, right? And the forecast does play out pretty much as predicted by the theory. The result happening according to the way the prediction was given gives confirmation that this is a good and a viable realm of theory, of scientific theory. If meteorology and weather science was just a guessing game, then the weather predictions would generally not bear out truth. But although there sometimes are exceptions to the accurate predictions given there, they're mostly correct. And doesn't that show us that we're not just reaching around in the dark and guessing about weather, but that we have a clear scientific comprehension which issues in accurate predictions? Or another case, to be even a little bit more expansive, do we know the exact date and time of, let's say, the next solar eclipse, or even the times and places where you'll be able to watch it from the surface of the Earth under an ideal viewing condition? Yes, we know that well in advance, years, even decades in advance. We can say, for example, the exact date at which Halley's Comet will pass by again the planet Earth, where you'll be able to view it at those times. And everyone's ready, right, with their like little eclipse viewing goggles when these things happen, because it's not something that catches us by surprise, but which is well predicted by the astronomers that observe the orbits of celestial objects and their movement. So when those predicted eclipses then happen on the exact date and time suggested by a theory, it again grants credibility to those scientific bodies of explanation. So the better and better that a scientific theory can predict accurately future outcomes, then the more likely it is to be true. And that's yet another feature of a scientific theory that adds to it being considered good. So at the very end then, there's only this last thing from chapter 12. At the very end, they talk about pseudoscience. And I just want to quickly tell you guys what that word means. Pseudoscience. The word pseudo just means false or fake. So literally, pseudoscience is just false or fake science. And you could say it like this, as the textbook describes it. It is a body of explanations that masquerades as science. So like puts on the false appearance as though being scientific, but it's actually not. A body of explanations that, using their language, masquerades as science, but it's not really. And what are some examples of pseudoscience? Well, there's astrology, the horoscopes. There's, tarot cards. There's palm reading, crystal ball gazing, the prophetic predictions of Nostradamus and stuff like that. All of that is totally pseudoscience. Numerology, the belief that numbers provide some type of occult insight into the way that things will play out. We can tell that these are all pseudoscientific because, number one, they make predictions in such vague and unclear language that almost anything can be given as a case of confirmation. If you've read the works of Nostradamus, which some people pseudoscientifically believe are accurate predictions of the future, the language used is so non-specific that almost anything could be assigned to it. Like they said that he predicted 9/11 when he wrote this: "Fire of the center of the earth shall make an earthquake of the new city. Two great rocks shall long time war against each other, and after that they shall color red the fresh water." Now, how can anybody seriously take that to be a prediction of specifically 9/11? Any event having to do with war, blood, conflict, could have been traced to something as vaguely stated as that. And if you say, no, I don't believe that this is confirmed by the events later, they'll just say, oh, you're not interpreting the script the right way. So pseudoscience literally means fake science. To avoid falling for the empty promises of pseudoscience, make sure you know how to critically evaluate scientific claims. If something cannot be falsified, if there are no new experiments or tests that are conducted in order to verify them, and if they don't admit of falsification or disconfirmation, then that can clearly be seen as something that is unscientific pseudoscience. And it's sad because a lot of people hold superstitious beliefs and they give their money, their time, their attention to these pseudoscientific fields that are propped up completely on no empirical study or investigation. So we shouldn't be so gullible as that. This is a critical thinking class, and I can't permit you to just feel at liberty to think that if you read the horoscopes, you're doing something rational that's based on science. Science is not just mysterious things that smart people know about. It's grounded in a specific procedure where you observe facts, you create hypotheses, and then you use tests to determine whether they're true or not. But where no tests exist and where no falsification is possible because of the wording of these postulated hypotheses, then there's no scientific claims to evaluate, even though they try to look as though they're scientific. And a person might even say, look, I'm a paranormal specialist. I've got these measuring instruments that can tell you how many ghosts there are in your area or whatever. If you deny that there are such things, then they maybe will say, oh, you don't believe in them, so they don't show themselves to you. Once again, that deprives you of the potential for falsification. So if someone's telling you here's something true, but nothing you do can possibly show that it's not, that's not a scientist speaking. The scientist invites you to test their theories, and if there's falsification, they're not going to just hold on to the theory come what may, but try to provide the correct explanation until you get the proper fit between test results and hypothesis. So just understand that we have to be able to distinguish science from fake science, and that's part of the point and goal of this class, along with all of our other important goals. So we finished now chapter 12, everybody. We got through all the notes right here towards the tail end of today's class period. So I'll just say have a great weekend. Look for my titanium announcement later in the weekend around Saturday or Sunday morning, and then you can check for your grade on the last homework you just submitted. And then just be ready on Monday. I'll send around the quiz for chapter 12 just prior to class time, and you guys will have the class period to send back the answers to me. So, all right, everyone, take care, stay critical, and have a great weekend. I'll see you back on Monday. Or you're taking the quiz on Monday. So last thing is this. Just understand quiz Monday is not a lecture day. So you'll just take the quiz, return the answers to me, and we'll resume lectures next live stream a week from today. That's April 22nd. Okay, guys, take care. Thanks again. Have a good one.